finding.
Yeah, so don't hardwire prime numbers. Write some code to test to see if something's prime, and use that. But there's two direct approaches. One is to go through your primes and subtract them in order from the number you're testing until you get something that's prime. The other, which may be easier but is much less efficient, is just subtract all your odd numbers, right? And then check to see if the number you subtracted and the number you're left with are both prime. But that's just doing extra work. Because if you try to do 52 minus 9, it doesn't matter what we get here, this isn't prime, so that's not going to satisfy. So do this until you find two primes, and then add 2 to this and start over again. 54 minus 3 equals 51, that's not prime. 54 minus 5 equals 49, that's not prime. 54 minus 7 equals 47, that is prime. For now, 7 plus 47 equals 54, and go on.
So for the number you're subtracting from your initial value, you want to basically just start and then test if that's prime, and then test if your result is prime. And if both are true, then you're good.
Then you're good. And if you run out of numbers, if you get down to 54 minus 51, right, so this isn't prime. If you run out of numbers, then you've proven that Goldbach's conjecture is false. So print it out in big letters and record the date and all the newspapers. All right, in your submission, again, I want a PDF file which contains your source code followed by the output. So take your source code, paste it into a document file, run the program, grab the output with your mouse, paste that into the file, export it as a PDF. Word or OpenOffice or any tools like that will save as a PDF.
Do you like syntax highlighting, or is that?
Sure, that's fine. Yes?
It also says to include output for 100 even numbers, beginning with 1 million.
Right. Yeah, that's these things. So write down 1 million equals some prime plus some prime. 1,000,002 equals some prime plus some prime, all the way up to 1,198 equals something plus something. So you have 100 lines of output. Put those into your PDF file and submit that.
Thankfully, it would just be a PDF, because if I had to print it out, then it would use up a lot of ink.
It would, and a lot of paper. So you can set something in your program to stop when it gets here, or you can just Control-C it. And if you've got spare cycles, just let it run. See what you find. I think Goldbach's conjecture has been verified up to some ridiculously large number. But 2 to the 4 million. Cool. Alright, so that's a PDF uploaded by the start of class on Friday. So other questions? So I'm going to do your first in-class quiz on Friday. I mentioned that yesterday. And it's going to cover set theory stuff, propositional logic, and the number theory stuff that we covered last week. Modular arithmetic, Fermat's little theorem, prime numbers, doing operations, modulo something. That's basically it. So some combination of that. I'll try to time it for about 50 minutes, but I'll probably give you the whole period, unless everyone finishes in like 5 minutes. All right, so we were talking about crypto systems. And we talked about shift ciphers, where you just add or subtract something to each character. We talked about transposition ciphers, where you just rearrange letters. And there's more sophisticated ciphers that you can use. There's one-way ciphers, or one-way encryptions that you can encrypt, but you can't decrypt. These are really good things.
What's the point of encrypting something if you can't decrypt it?
So nobody can figure out what you encrypted.
But,
Because if there's a way to decrypt, somebody might be able to figure out what your password is, for example.
well, it's
How,
one
how,
way.
can, how can you decrypt it if no
You
one-
don't.
Sorry, you mean like hash functions, right?
Yes.
Oh.
So for example, you want to log into a system. So you type in your super secret password. That's one of the most popular passwords still.
Topped only by password.
Password and ABCXYZ. And for some reason, baseball is always in the top 10. I don't know why.
Dragon? Something related with dragon is in the top.
Oh, really?
I thought it was unicorn.
Unicorn, that's a good one. So you type your super secret password in, right? And over here is your, this is the target machine you're trying to log into. And it has a database. And in here it says Nick, and your password is 12345. And you don't want that file containing your password, because somebody comes along in the middle of the night and they take this disk and they pull it out under their pocket and they walk back to their car and drive away. And now they can say, hey, Nick's password is 12345. And that happens to be the password I use for all of my money management funds. And so now people can like steal all my money. So what you do is you type in 12345 and it goes through this one-way encryption. Some mathematical function that takes 1, 2, 3, 4, 5 and generates $! Exclamation 4, 5, 4, 4, 3, number sign 2Z, @ number sign exclamation. And that's what gets stored in the database. And if somebody steals this file, they see this. You can't type this in and get into my account. Because when you type this in and it gets encrypted, it's not going to give you this. You have to type in 1, 2, 3, 4, 5 in order for it to be encrypted and give you this. So when I type in a password, so I'm trying to break into my account, so I try password, and it goes through the one-way encryption. It comes out as -- exclamation 34 -- number, and it says, nope, that's not the right password. And the only way it will let me in is whatever I typed has to turn into this exact string. But if I forgot my password and I call up the company and I say, can you look up my password for me? They cannot tell that this is how you get this. Okay, it's a mathematical function that it's easy to go from here to here, but it's practically impossible to go from here back to here. That's what you want your password security to be. Because if there's a way to go from here to here and somebody steals this disk, all I have to do is analyze the code, figure out what this function is, and then apply the inverse function to get from here back to my password. So you don't want plain text passwords, and if you're working with some entity and you say, I forgot my password, and they can send you your password to you, they are not secure. Chew them out, right? And there's websites you can post addresses for websites that have plain text password policies. All right, so that's a one-way encryption. Did you have a comment on that?
I was just going to say how do rainbow tables work?
How do what?
Rainbow tables.
What's a rainbow table?
You have a hash of something, and you take the hash of that, and you take the hash of the hash, and eventually you get the whole loop.
Oh.
And then you get a really nice way to break rainbow tables.
Yeah, you can set them up to work like that.
Are you sure? Because I was under the impression that rainbow tables were basically just a big fat database of plain text strings into a hash.
That's a hash table.
Oh,
A rainbow
okay.
table is a big old loop.
Big loops. I think you have to work to make that.
No, you don't generate them yourself. You actually.
But you also do other things like you add salt to these.
Well, hash and salted. Yeah.
So you take the system time and the process ID and the phase of the moon, and you come up with some randomish string that you pad onto this or use to manipulate it, and you store that, but it stops you from being able to as easily recognize patterns between passwords and encrypted passwords. And the encryption algorithms are public domain, right? And the passwords themselves are freely available on Unix, or at least they used to be. There's a file called etc/password, and you could see people's encrypted passwords in there. But it still didn't help you actually get into somebody's account.
Now it's easy.
Now it's all,
Now it's shadowed. You can't
Yeah.
see it.
Well, why can't they just like take the inverse of that function and do it?
because it's a function that's designed to be non-invertible.
I can answer that question.
How is that possible?
Okay, picture this, all right?
Go for it.
Okay, all right. Imagine, I'm going to define this function real quick. I'm going to give you a function that does this job. Okay, so imagine we have our password, and it's ABC, and we convert this to the numerical values according to the alphabet. So we get 1, 2, 3. That's our new digits. And then our function here is to just sum up all those digits. So we end up with 6. This is that. So let me ask you this. If I told you 7, what was my password? Assuming that I summed up all the numbers in it to get to there.
Do I know how long it is?
Nope. All you know is 7.
Okay.
Even if you did. Here, it's 2 characters. Which one is it? Is it CD or DC? It's exactly that concept.
Right. Good example.
But couldn't they use that to like make it easier to brute force?
Well, I mean, if it's just summing the numbers up, that's pretty terrible.
Yeah,
It's
so
probably
that,
not just
that
something,
and you actually end up with multiple passwords, like DC or CD would both get me in there.
Exactly.
But if you use a more complex function, and here's a really nasty function, take each character, take its ASCII code. If its ASCII code is 65, take the 65 millionth prime. If its ASCII code is 82, take the 82 millionth prime. Multiply those prime numbers together, store that in here. Multiplying prime numbers is easy, factoring big numbers into primes is difficult. And so you can add more layers on that. You can bump it up by the position in the string and so on and so forth. And the creation of these one-way functions is a huge branch of mathematics, a separate branch of mathematics that feeds off into all kinds of wonderful things. So let's talk about public key cryptography. So public keys are decryptable, right? You have a message, and you're going to go through some encryption to come up with E of M. And then you'd like to be able to go through some sort of decryption, a different function, that brings you back to M. So here's my credit card number. I want to send it to Amazon. So I encrypt it. I send gibberish over the insecure internet. People pick it up and listen to it, and they're just seeing gibberish. And if they don't know this function, they're stuck with gibberish. If they know this function, though, they can take that gibberish, turn it back into my credit card number. So a public key system, we can publish this, and we can keep this private. And this does not tell you anything about this. Okay, a shift cipher, the encryption is just add 6, therefore the decryption is just subtract 6. If you know how to encrypt, you know how to decrypt. But with a public key system, if you know how to encrypt, you don't know how to decrypt. There's no way to get easily from here to here. So this is public. This is private. And it comes down to products of primes. So this is not like something that we tested on the details of, but let me just show you a high-level view of how this works. So M is your message. And let's just suppose your message contains only uppercase letters. So just characters A through Z. And we're going to code them as follows. A equals 0, 0, B equals 0, 1, and so on. And Z equals 2, 5. So we're going to take your message, we're going to turn it into a sequence of these numbers. And we're going to break it into blocks. And there's an algorithm to decide how big these blocks should be. I'm not going to worry about the details of that. I can tell you offline if you want. But you break your message into blocks. So you have some string of digits. Okay, and that's what M is going to be. So M is some big long number. All right, pick and fix two large primes, P and Q, really big primes. And N is their product. So we pick a large integer e, which is relatively prime I'll tell you what that means in a second. Relatively prime to the following product, p minus 1 times q minus 1. And almost any number we pick is going to be relatively prime to this product. So two numbers are relatively prime if they have no common factors. Okay, so 20 and 18, they're both divisible by 2. So they're not relatively prime. 20 and 25 are both divisible by 5, so they're not relatively prime. 20 and 27 are relatively prime. This is only divisible by 3 or 9, and this is only divisible by 2, 4, 5, and 10. So there's no common factors. So we pick an integer e that's relatively prime to this product. All right, so when you want to encrypt your message, we're going to get some ciphertext C, and it's just M to the E modulo N. So take your message, raise it to this power, reduce it modulo N, which is the product of these two primes. So to do this, all we need to know is E and N. So your public key is just this pair of integers, N and E. So you tell the world when you want to send me a message, use this algorithm, use this value for N, use this value for E. And they can take their message, turn it into a string of integers, raise it to the power e, reduce it modulo n, and it gives them a big long number. That's how they code that piece of text.
Could you end up with the same thing?
The original text?
What?
Could you end up with the original text?
Could you end up with the encrypted text but with a different original text?
I think so. I think it's many to one.
Is that a problem?
I don't think so. Because the space of possible messages here is huge.
I'm pretty sure once you start decrypting it, you're going to decrypt it into different things too.
No, it has to be unique because you can decrypt. So different messages should give you different encrypted versions. Right, because we're limiting our message to n of these, so it's 2n digits, and that's going to leave us with the same thing. So that won't happen. All right, so we have this ciphertext C. Yes?
This might be kind of a big question.
Okay.
But, so say Amazon publishes their public key, right? what's the method that they would keep the private portion of that hidden?
I don't know. I've wondered about that.
Yeah, because, I mean, it seems like that's what you would want to get, right?
Yes, if
So-
you can get that, you can
You're
crack
good.
it.
Right.
And I don't know what kind of security is involved in protecting that.
I know, I mean, not Amazon, but Google,
Right.
they have their, I mean, this was on the Google Webmasters website. They have their encryption keys stored in a locked room in their data server, which requires 3 keys, one from each vice president of the company.
Cool.
So
Yeah.
that's how you get in to get their private
So
key.
low tech too.
But
So
those
those-
keys are on computers somewhere,
No,
and that's what I'm wondering about the security of.
Right, that's the catch. What you haven't touched on is signing yet, but
Right.
as I understand it, what they do is they take those keys and they sign other keys, verifying that those ones are also
Okay.
authentic. Which means that they can use the other ones.
Right. And if those other ones get compromised, they can just
They can
switch
issue
to
a
other ones.
revocation certificate saying that these ones are no longer valid.
Right. And signing, we're not going to talk about signing, it's the same idea. It's a way that you can validate that a message comes from a certain source, and you can use it, the idea of public keys and private keys, to do that as well. Because only the person who knows the private key can create these signatures, but you can validate that this was signed without knowing the private key. Yeah.
So why does this work to make the private decryption separate? Like, what about?
Well, let me
doing
show you
this
how you
prime?
decrypt, and then we'll see why you can't decrypt unless you know something ahead of time. Okay, because all we've talked about so far is how do we encrypt the message? How do we get this? And this is the thing that goes out over the insecure network. So given C, how do we find M? How do you recreate M? And it's going to turn out we can only do that if we know P and Q. And the public key has the product of P and Q, but it doesn't have P and Q themselves. Now, if you can factor this into the 2 primes that gave you this, then you can decrypt the message. But if this is a number with a gazillion digits, right now it's very difficult to turn that into 2 prime numbers whose product is n. But if somebody finds a good way to factor large numbers, all this falls apart. And that's part of the excitement of quantum computing and DNA computing and stuff like that.
Then they're going to just have a couple times to try that. Otherwise, the system
Yeah.
doesn't let them.
Right. You only need once if you know what the password is, though. And it may already have been cracked, for all we know. Because if you do find a way to crack this, you're not going to go to Amazon and buy stuff with somebody else's credit card. Right? You're going to sit on it, and you're going to use it to snoop on nations and governments and tap into their secrets and build information dossiers and things like that.
They're on the
So-
payroll of no such agency.
Yeah.
I was thinking like most of these hackers doesn't use these algorithms. So I was thinking about retail stores.
Mm-hmm.
Some of those, like all those, has a small device, handheld devices.
Yeah.
Do everything with that, and they have some extra access other than like normal employees.
Mm-hmm.
They just enter the password,
Right.
and they are written in .NET, so we can easily
Yeah.
use Reflector, get the connection string.
Mm-hmm.
There you go.
Yeah.
You just need to borrow that device.
Yep. And presumably someone can figure out how that device is designed and replicate the design.
Most of them are Windows Mobile, so
Yeah.
easy to crack.
Right. So yeah, this there's a lot of weak links, and the weakest link is the one that will bite you. But in an ideal situation where everything is secure, we get to this situation where we're given the encrypted message and we want to recreate the original message. So if you know P and Q, you can do this really easily. And this is where some number theory comes in. So we've encrypted by raising M to the E. Okay. If you know P and Q, there exists a D such that D times E congruent to 1 modulo p minus 1 times q minus 1. And that's a theorem that we haven't gone into the details of, but this is easy to do. If you have a number e, you can find something that multiplied by e will be congruent to 1, that modulo. So since d is congruent to 1, modulo p minus 1, q minus 1, de is one more than a multiple of this modulus, which means it's equal to 1 plus some constant times p minus 1 times q minus 1. That's just the definition of modulo. So if I take c and I raise it to the power d, that's c to the 1 plus k times p minus 1 q minus 1. And c itself is m to the e, so this is going to be congruent to m to the e raised to the 1 plus k times p minus 1 times q minus 1 modulo n. And remember, n is p times q. Well, we haven't talked about this, but if a is congruent to b, modulo p times q, then a is congruent to b, modulo p, and a is congruent to b, modulo q. And that's just definitions. This is saying that a minus b is a multiple of p times q. A minus b equals L times PQ, which means a minus b is a multiple of p, and a minus b is a multiple of q. So if a is congruent to b mod pq, a is congruent to b mod p and mod q individually. So given this fact, we can say that our ciphertext raised to d will be congruent to m to the e to the 1 plus k times p minus 1 times q minus 1 modulo p. So c to the d equals m to the e to the d equals m to the ed equals m to the 1 plus k p minus 1 q minus 1. So this is that e got absorbed. Right, so c to the d is m raised to this power, which is m to the 1 is just m, and m to the k times p minus 1 times q minus 1, all modulo p. And now we use Fermat's little theorem, and note that m to the p minus 1 is going to be congruent to 1 modulo p. So this is congruent to m times m to the p minus 1 raised to k times q minus 1 modulo p, and this is congruent to 1 by Fermat's little theorem. And so this is congruent to m times 1 raised to the k times q minus 1. And 1 to anything is just going to be 1, so this is congruent to m modulo P. And we can repeat the whole argument for modulo Q and show that C to the D is also congruent to M modulo Q. Last step. C to the D is congruent to M modulo P. C to the D is congruent to M modulo Q. P and Q are both prime, so they're relatively prime. And Chinese remainder theorem, which I mentioned but we didn't go through the details, says that therefore C to the D is congruent to M modulo P times Q. Which is modulo N. So if we take our ciphertext, we raise it to the power D, and we reduce it modulo M, we get back our original message. So that's all proof that you can do this. The solution is simply take your ciphertext, raise it to this power, reduce it modulo N. But we were given this as a public key, and this is our private key. And we can find D if we know P and Q. If we don't know P and Q, it's very difficult to find D. So publishing N and E as our public key doesn't give somebody information on how to find this, which is what they need to decrypt. So I'm not expecting you to grok the details of that, but I wanted you to have seen it. And you can actually do this with short messages yourself. You can pick small primes and go through the process, and that helps nail it down.
So the only part I was a little shaky on was
That's pretty good.
just one part, really. On your second line there, on the left side, where you've got m times m to the k times p minus 1 times q minus 1, you kind of absorb the p minus 1 down into an exponential. What was that theorem there?
So this is just m to the ab equals m to the a raised to the b.
Right.
Yeah.
Okay, cool. That's all.
Yes, that
Well,
works.
no, the rest of it actually, I think, makes sense.
Cool.
I think.
Just try it with the small primes, I'm serious.
Yeah,
It does help
it's
it make
fun.
some sense. But please, do modular exponentiation. Don't
Yeah.
try to do it directly. I was
Right.
wondering why my algorithm was still running 5 minutes later.
Yeah.
When,
And this is why modular exponentiation is useful for this, because d is going to be a big number, and you don't want to multiply c by itself that many times, because c is going to be a big number. But we can use those tricks we saw yesterday with modular exponentiation. Write d out in binary, just find the powers of 2, powers of c, and then multiply them together.
How did we get modular to 1 with Fermat's little theorem over there?
Because Fermat's little theorem says that any number to the p minus 1 is congruent to 1 modulo p, where p is a
So we just
prime.
did that twice, right?
Yes, we did that to change this. M to the p minus 1 mod p is 1. And so it's 1 to the k times q minus 1, and 1 to anything is just 1. M is just m, so this is congruent to m. And then we can do the same thing with q, q, q. M to the q minus 1 will be congruent to 1. 1 to the k times p minus 1 mod q. All right, so this stuff works, which is good. Because I like buying stuff at Amazon. And it's one example, and this is called RSA. The name of the 3 mathematicians, 1 faculty member and 2 grad students, I believe. Berkeley and I think Stanford were the institutions involved, and they came up with this algorithm quite a while ago. And as they were in the process of publishing it, they were getting good neighbor checks from the government saying, let's talk about this, we don't want you to publish this. Because this was a game changer, basically. I mean, it completely changed the scope of privacy and security. And they threatened them with fines and jail time if they went public with this. And Berkeley told the people there, if you're brought up on charges and you have to go to court, we'll cover your court costs and we will defend you. And your right to publish this as part of academic freedom. If you go to jail, we can't go to jail for you. And if you're fined, $1 million, we can't pay $1 million in fines for you. But we'll support you if you want to go forward with this. And so they sent their paper into a conference, and they went on stage to present it. And everybody knew the story, the backstory here, so it was fairly tense, I'm told. But the advisor asked the two graduate students to sit on the side of the stage. And the advisor himself decided to do the presentation in case things happened. And he went up and he presented the results, and nothing bad happened. So this went into the public domain at that point.
When was that?
I don't know if it was RS or A. You can Google them. Google RSA, you'll see the three names. When it was? I want to say 70s. I don't know if that's right. That sounds pretty early, but that's stuck in my brain. Let's see. So yeah, you can do interesting things with
77.
mathematics.
RSA
1977.
First published.
Yep, Rivest, Shamir, and Edelman. Still gotta tell him to clean the filter.
Another guy came up with it first in 73, but it wasn't declassified until 97.
Okay.
Well, an equivalent system, but
Yeah.
True. I don't really know what that means.
I don't know.
An equivalent system.
It says first published 77 though.
What's the footnote?
That's just a reference to it.
Yeah.
Clifford,
Yeah, what did he...
Bristol University. I don't know. We can look it up. All right. So I think that's all I wanted to say about number theory and primes and applications and stuff like that. I want to go back and pick up 3 topics from earlier in the term that we kind of skipped over in the interest of momentum. And you've encountered these things before, but I want to put them down in a little bit more of a specific way. The first thing is this idea of summations. So I think you've seen these in other math courses before. If we have a sequence of numbers like A1, A2, A3, A4, A5, and we want to add those together, we can just write a shorthand like the sum from I equals 1 to 5 of A sub I. And it's a shorthand for that expression on the right. And the first thing I want to point out is that if I had written this, it's exactly the same expression. The meaning of it is exactly the same. It's going to be A1 plus A2 plus A3 plus A4 plus A5. The choice of this index variable is arbitrary. It doesn't show up in that expression on the right. It's just a placeholder, and I'm saying as that placeholder ranges from 1 to 5, plug it in here and add them up together. And sometimes we can write it like this, put a range of values on the bottom of the summation. And And so this thing is called the index of summation. And if we code something like this, it's the index of our for loop usually. So we can say things like sum from I equals 1 to 3 of I squared. And that's just equal to 1 squared plus 2 squared plus 3 squared, which in this case is 14. We could say, what's the sum from j equals 5 to 7 of j? And that's just 5 plus 6 plus 7, which is 18. Okay, so you're familiar with this notation concept, right? You've encountered it before. Some things to note. So this is A1 plus A2 plus all the way up to A sub n. If I wanted to sum up k times each of those elements, I can pull that k outside like that. And that's just algebra. So we can pull constants out, assuming k is not changing during the summation. And we can also say things like this. If we're summing a set of elements where each element is ai plus bi, we can sum the AIs and then sum the BIs and put them together. And that's also algebra. If you write those out, you can see that you can rearrange the elements and get the two summations on the right. The other thing we'll encounter is a change of this index of summation. Suppose we want to add this series, the sum from I equals 0 to 3 of I plus 5. So this is 0 plus 5 plus 1 plus 5 plus 2 plus 5 plus 3 plus 5. But we can rewrite this expression by changing our index from I to something else. What I can do is I can say let j equal I plus 5. And now I'm just going to sum up j. But when I is equal to 0, j is going to be 5, and when I is equal to 3, j is going to be 8. So I can simplify this expression, sum of I plus 5, into just a sum of j by changing this index of summation to go from 5 to 8 instead of 0 to 3. And you can see why that's happening. This is exactly 5, 6, 7, 8. But if this was a more complex expression, I may be able to do a more complex substitution. But does everybody see where this is the same value as this? Say yes or no?
Yes.
Okay. So let me leave you today with one particular sum that will come up fairly frequently. So let's do the sum from I equals 0 to n of r to the I, where r is some fixed number. And we'd like to find an expression for s sub n. Let me just call this s, so we don't think we're multiplying. Sum from I equals 0 to n of powers of r. And there's a trick we can use to find the value of s, which is multiply both sides by r. And we can bring this r inside. So we're summing r times r to the I, which is the sum from I equals 0 to n of r to the I plus 1. Because r times r to the I is just r to the I plus 1. Which is the sum from 1 to n plus 1 of r to the I, which is the sum from 0 to n of r to the I plus r to the I plus 1 minus r to the 0. So this gives me everything from 0 to n. This adds r to the n plus 1, and this subtracts the r to the 0 that I didn't want to start with. And this sum from 0 to n is just s. And r to the 0 is just 1. So we have r times s equals s plus r to the I plus 1 minus 1. We can subtract s. And we can factor out an s. And we can divide, and we get a nice formula with no summation involved. So the sum from 0 to n of r to the I is just, I lost my I somewhere. This is n plus 1. Right, we need to add an extra n plus 1. So that's an n. So the sum from 0 to n is just r to the n plus 1 minus 1 divided by r minus 1. And the classic example would be like r equals 1/2, or r equals 2. All right, we'll look at that again tomorrow. We'll look at double summations. Then I want to talk about functions, and I want to talk about matrices. And then we're on to induction. Good stuff.
Which is that what you were nervous about?
I said it was glorious, I think.
You also said it was probably the hardest thing in this class.
It's a conceptually challenging concept.
So yes.